Just a quick glance at what we've covered so far. We started off by introducing the notion of limiting value for functions. So we talked about the limiting value of a function f of x as the argument x approaches some point A. These functions are real valued functions, functions defined on the real numbers, or maybe some restricted subset of the real numbers, and taking values in the real numbers as well. Okay? So-called real valued functions. So this is referring to the limiting behavior of f of x as x approaches A, and it's claimed to be equal to some value L. This is just an alternative way of writing it. F of x tends to L as x tends to A. Now, we didn't give this a very rigorous definition in terms of epsilons and deltas and so on. We just stuck with this kind of, what it means is the values f of x are getting closer and closer to L as x gets closer and closer to A. Okay, well, we accept that that's a not very rigorous definition. It's not incorrect or anything. It just doesn't say enough detail about exactly what the rate of convergence is. Okay. And then we had the related notion of continuity. Oh, so and importantly, then we had an algebra of limits theorem for the behavior of limiting values of functions. Okay, which is very much the analogous thing to the same named result for convergence of sequences that we looked at in early on in the first term. So linear combinations of functions, products of functions, quotients of functions, they all converge to the appropriate thing if the ingredient functions, the f and the g here, if they are converged, they have limiting values as x approaches A. Then so will those various combinations. And maybe with the last one, you got to make sure you avoid 0. So probably g of x has to be non-zero in some neighborhood of A, and yeah, non-zero in some neighborhood of A, I guess. We're avoiding 0 anyway. And we have something which we mentioned here. We have L'Hopital's rule, which it's kind of awkward we're mentioning it here because it features the derivative and we haven't yet come on to the derivative. But it is important for calculating limiting values, so it did get a mention here. Okay, then we talked about the related notion or the connected notion of continuity. This was nice behavior of a function. This was where the limiting value as x approached an argument A, not only did it exist, but it was actually equal to the value of the function f at A itself. This is the definition for the function f being continuous at the point A in its domain. To say a function is just continuous probably implies that you're saying it's continuous everywhere in its domain. The definition refers to a particular point. So this is f being continuous at the point A. Now this one we did give a formal definition to. And the formal definition is very much the analogous thing to the formal definition of convergence for functions. This here in this displayed equation here is the formal definition of continuity. So this function f is continuous at this point A in its domain if for any value of epsilon, which is a interval around the point L which is equal to f of A, for any size of interval around that point L, you can find a corresponding interval here such that f maps this interval completely inside the interval around L. That's what this is saying. For every possible value of epsilon, positive epsilon greater than 0, there exists a corresponding delta such that x minus a less than delta. That's saying that the argument x is within this interval. The distance between x and a is less than delta. That implies the distance between f of x and f of a, which would be this kind of distance here, is always going to be less than that epsilon. And if such deltas can always be found for any positive value of epsilon, the function is continuous at the point A in its domain. And we used that definition to be able to prove part of Theorem 4.3. Theorem 4.3, it's the usual kind of structure referring to how the operations we can do with functions, addition, multiplication, quotient, and so on, how they preserve this feature, this property of being continuous. So we proved that given any pair of functions f and g, that the product function f times g will be continuous at a. Okay, we proved that last time. The proof is in the notes for the linearity part. So if f and g are continuous at a, so is the linear combination alpha f plus beta g. Definitely read through and study that proof. And it's left as an exercise for you. And I've referred to it again here, I think, here in the new tutorial sheet I'm going to give you. To prove that continuity is preserved by quotients as well. And that's again, that can be, as it says here, it's similar to the case for convergence of sequences. So when we proved that a quotient of sequences was convergent to the quotient of the limits of the numerator and denominator, the technique of proof there is similar to what you need for proving that the quotient of functions will be continuous at the point A if f and g are continuous. Okay? So that's one of the exercises that's in the new tutorial sheet. And there's also a theorem about how composition of functions preserves this concept. So continuity underlies the notion of the derivative. Okay? So that's what we're coming on to now. So we're talking about real valued functions, functions defined and the real numbers taking values in real. And the kind of visual device we imagine for these functions is the graph of the function. So here's a typical function f here, and its graph is shown with this black curve. Now the derivative of the function is a device for talking about and representing how the function is changing. Okay? How the function is changing. Now one very basic way you might describe how the function is changing is to look at 2 points in its domain. Okay? A point A and a point X in its domain. Okay? The function will take various values, so it will take a certain value f of a here, and it takes what looks like a larger value here, f of x at the point x. And you can ask yourself, what is the change in behavior of the function at a compared with x? Okay? So you're comparing these two values, f of x and f of a. So the natural device to use to compare those two values is to simply look at the difference of the two, f of x minus f of a. Okay? And how different is f of x compared to f of a? First thing you would think of is just look at the difference. Okay? What distance is there along the y-axis from f of a to f of x? And what's the measure of the difference? Okay? It's just the one value minus the other. But how much is the simple difference talking about the innate or inherent behavior of the function? Because, you know, if the x is a long way away from a, then the value f of x could change a lot. And if x is very, very close to a, maybe the function f won't have had enough time to change very much. Okay? So rather than simply looking at the difference of the two quantities, it is more appropriate, or it makes sense to examine the difference between the two quantities, but relative to the actual distance from x to a. Okay? Because if the difference between f of x and f of a is large, that could be because the function is changing a lot, or it could be because the value x is very, very far away from a. The function might only be changing very slowly, but because the x is way, way away from a, function f has, you know, passed through a lot of value and changed a lot from f of a. So if we want to talk about whether the function is increasing or decreasing a lot or changing a lot, we ought to look at this difference, but make it relative to the difference in the two arguments that we get. So we look at this ratio. So this is the relative change in value of the function f compared to the difference between x and a. Okay? This has geometric meaning. It's the gradient of this line here, this straight green line, which you can refer to as a chord across the graph. So it's going through the 2 points a f of a and x f of x. And the gradient of that line is also known as the tangent of the angle. And in terms of the triangles involved, so you can form a right angle triangle by dropping a perpendicular. So you've got this right angle triangle extending from the point a f of a up to x f of x. You've got a horizontal base along here. Okay, and the tangent of that angle is the ratio of the opposite side to the adjacent side. Remember, that's how the tangent trigonometric function is defined, ratio of the opposite to the adjacent side. Well, the opposite side of this rectangle, you could draw it into the diagram there in your notes. This rectangle hovering in the middle here, this right angle triangle, the opposite side is the difference f of x minus f of a, the length of that vertical side. And the length of the bottom side is the difference x minus a. Okay. Okay, I can hear people chatting all the time. These rooms are designed for sound to travel all over the place. So when you're chatting quietly, everybody can hear it. Okay. Thank you. Okay, so this is the change in value. We've now formed the relative change in value of the function x between two points in its domain. But that only takes account of the behavior of f at a and the behavior of f at x. And the function could be doing all sorts of things in between those 2 points. Okay? So yeah, it captures the comparison between the behavior of f at x and the behavior of f at a. But we want to get a device which is inherent to the function itself, and somehow captures this notion of what the function is doing at the point A itself. As you move away from A, the function might start to have other behaviors and may start increasing a lot or decreasing a lot. But we're trying to zero in and capture some measure of how the function is behaving at the point A. So a natural thing to do would be to move the point X closer to A. To get closer to A, to kind of zero in and remove any effect of what the function is doing away from A, and just get closer and closer to A and somehow capture what the function is doing at A. And that naturally suggests a limiting process. Okay, to let the to keep A fixed and let the second point converge to the fixed point A. So these lines, these green chord lines across the graph may change as x approaches A. The value of f of x is changing. The value of the difference x minus a is changing. So the green line may alter, depending as how that quotient alters, f of x minus f of a divided by x minus a. But in the limit, in the limiting case, as x approaches a, those green lines will, for a nice, well-behaved function, they could converge to some limiting line. So this limiting line is important. This is what's called the tangent line to the graph at the point A. Okay, and it still has a gradient. The gradient of the tangent line will be the limit of the gradients of the chord lines when you're forming between the value of x not at A. That gradient there. So that we're no longer talking about a second point A. We've taken the limit as x approaches it. So we've zeroed in on the inherent behavior of the function at the point A itself. Okay? And so this is what gives us our definition of the derivative. Okay? So in 4.3 there, we have a function is differentiable at the point A. If two things hold, we require the function to be continuous at A to begin with, and then we also require this limit to exist. Okay. Now, what do we take? We're taking the limit of the relative change in value of the function. The change in value of the function, which is f of x minus f of a, relative to change between x and a, relative to the quantity x minus a. So that ratio there is the gradient of one of those chord lines between the points a and x. And we're taking the limit of it as x approaches a. And if that limit exists, then this is what is known as the derivative of it. And we typically use two main types of notation to refer to it. We can refer to it as df dx, that refers to the general derivative, and you can put a subscript against it there at x equals a to mean we're talking about the derivative of the function at a. Or a more compact notation, kind of easier to do in some ways, is just to use a prime. If you've got a function and just a tick, a superscript tick on the function, you kind of read as f prime, or specifically as the derivative of f at a, you can use that notation as well. Okay. Now, just to say a little bit about some negative cases, about when might this limit not exist. So this is definition 4.3. So definition 4.3 of the derivative. So what kinds of function might not be differentiable? Okay, we've seen this definition. In a moment, we'll be working through some examples. We'll see positive examples of functions that are differentiable, and we'll obtain their derivatives. But it's also useful to look at things on the other side and say, well, when does this thing not apply, or when does this property not hold? Okay. So example 1, we can think of a function not continuous at a. Not continuous at a. Now, part of the definition, we required the function to be continuous at a. So let's imagine a function not continuous at a, and think, what might be the problem there. So here's our point A. Here's a graph of a function which is probably continuous everywhere else except at A. Okay, and what's applied? So there's an immediate, instantaneous, discontinuous jump in behavior, change in value of the function at the point A. Okay, you've got this left-hand branch and this right-hand branch. Well, if you look at what might be happening to the chord lines either side of this point, you see? The chord line from f of a, let's suppose that f of a actually has this lower value here. So we've got an open circle up here. This value here, so f of a is equal to L, this lower value down here. Then the chord lines, when you're talking about an alternative point here, are looking like this, and as x approaches a from this side, chord lines they are settling down, and they do seem to be settling down to some limiting behavior. Okay, maybe this kind of a line. However, when you imagine a point x to the other side of a, we've got very different chord lines. I'll do these in blue. Come out. So there's a chord line corresponding to a value of x to the right of a. And as that point x gets closer and closer to a, the chord lines are having a limiting behavior. You can kind of see they're getting steeper and steeper, and the limiting behavior of these blue chord lines is going to be probably a straight vertical line, which is very different to the limiting behavior of the chord lines as you approach a from the left. Okay. So you can see here you've got different limiting behaviors of the chord lines depending on how you approach a. Depending on how x converges to a. So there's no unambiguous single limiting behavior of the chord lines. So we say here that f is not differentiable at the point A. Now you can kind of weaken the definition or split it and kind of make it a bit more technical. You can speak of a left-handed derivative and a right-handed derivative. You can make sense that way, and this function would have different left and right-handed derivatives. At the moment, we'll just speak of this kind of single concept. So because this function is not continuous at A, there is no single limiting behavior of the chord line. So there's no single kind of measure of how the function is behaving at A. Because it's making this awkward, instantaneous, discontinuous change in value. So another example would be a function that would be continuous at A, but still not differentiable. So we want a function that's continuous at A, doesn't make an immediate jump in value at A. Still has something funny going on. So, ouch, there's a sharp point. The function is not making, it doesn't have a discontinuous change in value here, but it does kind of make a discontinuous change in its behavior. As you're approaching A from the left, you're kind of increasing. But then suddenly, instantaneously, you change to decreasing behavior. That produces that sharp point. Now, in mathematics, we do have a technical term, smooth. When you look into more general, when you look in detail at analysis and differential geometry, we do have the notion of smooth behavior and non-smooth behavior, and it roughly corresponds to differentiable. When stuff is differentiable, it's termed smooth. When it's non-differentiable, non-smooth. So this would be an example of a non-smooth point on the curve. And again here there is different limiting behavior. Different limiting behavior of the chord lines, depending on how x approaches it. You've got one kind of behavior as the chord lines approach A from the left. You've got blue, one-sided tangent line, so to speak. But if you approach A from the right, your chord lines are probably going to be approaching this red line there. Okay, different behaviors depending on how you approach that fixed reference point A. So again, this function would not be considered to be continuous, to be differentiable at the function at the point A. Probably differentiable elsewhere, but not at the point A. So let's look at some examples. These are talked through in the notes. So those are some negative examples, some positive examples. So some positive examples would be, well, consider the function f of x defined as k times x for some real value k, for some constant coefficient k. Is this function differentiable at some point A in its domain? The graph of this function is, of course, a straight line through the origin, straight line of gradient k. So we expect this to be differentiable. It's just got the one fixed increasing behavior, or decreasing depending on whether k is positive or negative. But we can apply the definition. So we can let A be any point of the domain. The definition of the derivative is this limit if it exists. Okay. Now, at the outset, this limit may or may not exist because we're familiar with the idea of limiting processes that do have limits and limiting processes for which there's no limit, no limiting behavior. So that's the definition. Now we have a definition for this particular function f. So this is the limit as x approaches a of k times x minus k times a over x minus a. Which of course you can see how this is resolved. You can factorize the numerator. And what we're doing is we're taking the limit as x approaches a of k times x minus a divided by x minus a. Now you can't use the algebra of limits theorem yet because both the top and bottom are approaching 0 as x approaches a. But you notice that, because x is never equal to a, x is just getting closer and closer to a. So these are always non-zero quantities, so we can divide above and below. We can just cancel them from the ratio, and this ratio is always the same. Well, it always has the fixed value k. And so what's the limit as x approaches a of k? Well, it's just k. So the limit exists, and it's always equal to k. So no matter what point a you take in its domain, the derivative of this function is the constant k. So this function has a constant derivative. We could look at another example. What's the second example? Is kx squared. So we could consider a function g of x being kx squared. And we could apply the definition. We could let a be a point in its domain. This function is defined everywhere. So the derivative of g at a should be the limit as x approaches a, g of x minus g of a over x minus a. That's just the definition of the derivative. So this is going to be kx squared minus ka squared over x minus a. So this is the limit as x approaches a, k times the difference x squared minus a squared over x minus a. Now again, we've got this 0 over 0 limiting behavior, it seems to be. Okay? But we can still resolve this in a similar way to before. We can divide above and below by this troublesome quantity of the difference x minus a. And the factor it leaves behind in the top is x plus a. Okay, why? Because x squared minus a squared is equal to the product x plus a times x minus a. Okay, so cancelling the x minus a from the top and bottom just leaves behind the x plus a. And there's no problem with applying our algebra of limits theorem about limiting processes there. It's just a limit of a constant multiplied by sum between another constant a and the quantity x. The limit as x approaches a of that, using our algebra limits, is simply k times a plus a. So in other words, 2ka. So that's using the algebra limits. Theorem. And this argument will apply for every point a in its domain. Okay? So the derivative exists everywhere. G prime A exists at all points A. And so we get a derivative function. Which has this defining formula. The derivative evaluated at any point x is 2kx. That's another positive example. Now, other functions which are other polynomial type functions, or other powers of x, can be handled in a similar way, and there's a question or two on the tutorial sheet. So other powers of x can be handled in a similar way. And making use of the factorizations. So what is xn minus a to the n? We can always factorize that at least in one step. We can always factorize that at least one step. We can always extract the factor x minus a out of that. The factor that's left behind is this quantity here. It's all possible products of x and a with integer exponents, where the total exponent is equal to n minus 1. So this continues n minus 3, a squared, xn minus 4, a cubed, all the way down to second last term would be xa to the n minus 2, and then the very last term would be a to the n minus 1. Okay, so we always have this factorization. Okay. Or a more compact way to write that is we can use a big summation here. Think of j as being the index on A. J goes from 0 up to n minus 1. And if you've got a to the j, then you've also got x to the n minus 1 minus j. So that's a more compact way of writing that second polynomial, just with the single summations. Okay. So this formula is a very useful formula to have. It should kind of be in your toolkit of things that you might deploy at various stages. Now, depending on what the value of n is, there may be further factorizations you can do with that second polynomial. But for working out derivatives, this one is one that always comes in useful, because it's one of the factors you split away is the difference between x minus a. So what about negative powers can be handled? Negative powers of x can be handled also. Beginning with, say, the function f of x, which is 1 over x, x to the minus 1. What is its derivative? Well, we can handle that in much the same way. The derivative should be the limit as x approaches a of what? 1 over x minus 1 over a over x minus a. That's what applying the definition of the derivative would be. F of x minus f of a, so 1 over x minus 1 over a, relative to the difference x minus a. Now, you've got to treat these fractions correctly. There's no cancellation we can see yet, but we can see what the correct factorization is to do. Is if we take this difference of fractions and write it as a single fraction. How do you add fractions? Of course, you want to put them over a common denominator. And the common denominator here would be x times a, the product of these two denominators. And then the numerator would be a minus x. Okay? That's what we have for adding those fractions. Subtracting them. Whatever. And really, this is the same factor, except it's just got a minus sign in front of it compared with that one down there. So you could rewrite that, just to make it obvious, as minus x minus a divided by xa over x minus a. So we can now do the cancellation. We can cancel that factor from the top and bottom of the fraction. And what we're left with is the limit as x approaches a of minus 1 over, see this denominator here is down here, x times a. And provided of course that a is not equal to 0, we're not approaching 0, but the point 0 is not a valid argument for this function anyway. It's not in the domain of the function. So assuming a is not 0, this limit does have a limit. It's minus 1 over a squared, providing that a is non-zero. Of course it will, because a wouldn't have been a sensible argument to give to f anyway to begin with. The formula 1 over x isn't defined at 0. So again, this function is differentiable. Okay? So f differentiable at all non-zero points. Giving the derivative function so we have a derivative function f prime of x is minus x to the minus 2. Or minus 1 over x squared. And all higher powers, higher negative powers, could be handled in a similar way, together with this factorization formula. And there are some associated tutorial questions based on that there. So that's a first look. So after these initial examples, we need to explore properties of the derivative. And that's going to occupy us next week. And we'll consider the standard basic properties that we need to know about of the derivative, and we'll supply rigorous arguments for proving some of them at least. Okay. So what are these? And I'll switch back to the notes to have our first look at some of these. So they are the ones we want to emphasize first. They're all about how do we relate derivatives of compound functions or complicated functions. How do we relate their derivatives to derivatives of their ingredients? Okay, it's that common theme. Algebra of limits theorem for sequences. How do we relate limits of complicated sequences to limits of their component parts? It's the same thing for algebra of limits for functions. Okay, so it's a common theme that's emerging all the time. And this is the subject of these basic properties of the derivative. Which on page 54 of the notes, so these are the ones we'll start to look at. Linearity. So the differentiation process is linear. What that means is that if you have functions g and h, which are differentiable. And you have a new function f, which is a linear combination of g and h. Then the derivative of f is the linear combination of the derivatives of bits in f, g and h. It's a very familiar looking result when you think back at our algebra limits theorem for convergent sequences. Derivative of a linear combination is the linear combination of the individual derivatives. We will also prove a product rule. But now we've got to be careful here because this is where the analogy breaks down. So the product rule does not look like the algebra of limits theorem for sequences. Sorry, where's my So I try not to write down false stuff, but sometimes it's good to write it down as a warning. So it is not true that the derivative, don't even take this down, or if you do take it down, put a big warning sign around it. So, but I see people make this mistake often. It's a common slip that people make. Because it kind of seems reasonable to say that the derivative of a product is the product of the derivatives. Because it worked for limits of sequences, it worked for limiting values of functions, but it does not work at all for functions. Okay, maybe in some some extreme circumstances or some very particular circumstances, but it is not true in general. But yet it is a common mistake that people kind of make unthinking. So what I've written there is that I've written the derivative of a product is the product of the derivative. It's false. It's not the case. Sorry, you can't see it there. But the derivative of a product is the product. Well, what I've written is that it is not the product of the derivatives. Okay. So we need a kind of rule to replace it, which is the so-called product rule of differentiation. There is a nice relationship between the derivative of a product and the derivatives of factors, but it's not as simple as that. It's this so-called product rule. So it's a combination of the derivatives. So if f is the product function g times h, then the derivative of f is the product of the function g with the derivative of h, plus the combination the other way around, the function h multiplied by the derivative of g. Okay, and we can prove that using the limit definition of the derivative as well. And then further on in the notes, you'll see results about something called the chain rule, which refers to compositions. Composing functions is a very important operation. We want to know how the derivative of a composition relates to the derivatives of the individual parts. And appearing afterwards, for reasons that will become clear, because it's the way we prove it, we have a quotient rule, which again is not the kind of naive quotient rule you might expect, like this. The derivative of a quotient is not the quotient of the derivatives. It's this more complicated combination. So here we have a function y, which is a ratio of two functions, u over v. And there is a relationship between the derivative of y and the derivatives of its parts, but it's not the simple ratio of them. It's this combination here, okay? which we'll be able to prove as well. Also appearing there, you'll see it, and we'll explore all these things next week. Is we've got an extract, these 2 pages, which appear on pages 52 and 53 of the notes. These are an extract from the standard mathematical formula book, which you'll have in the exam. And this lists a lot of standard functions down the middle, and their derivatives in the right-hand column, and their integrals in the left-hand column. Okay, so it's quite a useful table, which we'll refer to from time to time. We've already maybe proved some simple cases of some of these initial results. And it summarizes those rules about linear combinations, product rule, quotient rule, chain rule, and so on, sums and differences, the linearity. It summarizes those on the second page. So you should be familiar with these 2 pages. They'll be part of your toolkit for the exams. So I'm just going to finish. So we'll continue this story. We'll look at those properties of the derivative and supply arguments for them next week. And I'll just finish by handing out to you the next tutorial problem sheet. You didn't get the sign-in sheet yet. It's down here.